we missed the moon, we don't really care where it goes after that. So we can use trajectories that are a little bit different. And the key thing is the trajectory uses a little less energy than for the Apollo program. There is some interest in returning a rock sample from the moon, and the return from the moon is different also. The reason for that is we don't have to keep astronauts alive, so we can enter in a much steeper re-entry than was possible for Apollo. As far as the tools, there's not that much difference. I'll just emphasize again, we had to pretty much invent techniques on the fly because the computers were so new, but programs we got finally were pretty much the same ones we use today.
Any more questions?
Yes? No? If you've got any more questions, now's the time. Just come up, use the mic. Wow, stunned. Oh, we have a taker.
Hello, I was wondering, since there is no astronauts involved this time, is there some simplification you can do to the orbit, the trajectory, so that you don't have to have all the variables for a four-body problem? Or is there some simplification, or is the sun always involved, however you do it?
Yeah, I'm glad you asked that, because there are quite a number of simplifications. The easiest one is just to execute a two-body orbit. If you think about it, the perigee of ellipse needs to be near the Earth. The apogee needs to be, it has to at least reach the orbit of the moon. So if you design an elliptical orbit, that eccentricity, if you time it right, you'll find that you do hit the moon. It's a lot easier when we're just trying to hit it as opposed to swing back. Also, there's some techniques that we worked out. There's a thing called patch conic. You might be familiar with that. Sometimes it's called matched conic. It's used a lot for interplanetary missions. There's what they call a sphere of influence around the moon. And if you make the assumption, simplifying assumption, that outside that sphere of influence, motion is fairly two-body relative to the Earth, inside it's two-body relative to the moon, then you can't get accurate trajectories, but you can get very nice motions that you can use for parametric studies, that kind of thing. There's an even more interesting one, which I think I invented. Now, you never know about these things, but it's based on a very simple principle. Because this orbit is almost parabolic, the energy turns out to be dependent only on the angular momentum. So if you leave the vicinity of the moon with the right angular momentum, which of course translates to a velocity relative to the Earth, then you're going to re-enter at the desired altitude. And I'll mention that in Apollo 13, remember they had to do manual burns, manual mid-course corrections to hit the re-entry card. That's how that was done. It was done strictly by matching the angular momentum that they needed. Next.
Okay. Thank you very much. Okay, bye-bye.
Bye-bye.
Okay, I'm not sure about the schedule. As you've thought, we've got one part left in regards of the communications. Is this okay? I think it's 15 minutes, should be fine, no? Okay. And I'm pretty sure you will like this part. Whew, okay. Let's see if this works again. Oh, no, the mouse. Yeah, okay, special guest. So, 45 is absolutely perfect. I just need 15. Okay. That's okay, fine, perfect. Okay. As you can see right there, and now for something completely different. So, just get rid of trajectories and Google Lunar X PRIZE for first. And let's think about communication and how to do it a better way right now. So first of all, as we've developed a solution, I would like to start with the problem. So, what is the problem? Because if you don't have a problem, why develop a solution? It's because it's quite boring. So, okay, first of all, we have space. Well, space is always, it's big, it's really big. It's cold, and most important, it's empty. It's not 100% empty, but you've got a giant distance between stars, even between planets. So here we are, starting with our problem. Our first problem is distance. So just give you 4 examples. The first one we already know about is the distance between Earth and Moon. It's about 400 kilometers. That's fine, we've already heard that. Okay, so let's look at the distance between Earth and Mars. That's about 130 million kilometers. It's an average value because Mars has a relatively distinct rotationally distance fluctuations between Earth. There's a wonderful graphic on Wikipedia on this. And this is pretty cool. This is the distance between Earth and the farthest ever man-built object away from Earth still communicating with us. And it's 60.9 billion kilometers, if I'm correct, yes. It's Voyager 1. It's pretty cool. Okay, so why I'm telling you this? Because with distance, always there's a problem. The problem is not just mathematics, because I'm not so much into mathematics. So I try to explain you this equation a little bit with some graphics. So let's look at this. We have our Earth. Everyone knows it. We have the geostationary orbit. On the geostationary orbit, we have all the satellites you can communicate with to do the important things like watching DVB-S HDTV all day. So, communicating with this satellite is absolutely no problem. You can watch HD television, no problem, okay. So, let's look at something like this example. If we place this sending unit from the geostationary orbit in the orbit of the Moon, you will see that you need a 100 times more signal strength to get the same signal back to Earth. So, just to show you what this equation means, you can see, if you look at the distance, because it's factor 10, you can see that's 1 divided by r power of 2. So you see how the equation works out. So what does this mean? This extreme high factor, 100. Okay, let's look at the next slide and we'll see. Yeah, okay. Greater distance between 2 objects always leads to the fact that you need larger sending and receiving antennas. The interesting part of that is, it's not everyone thinks about antennas like the very large array in New Mexico. We have this very big high gain antennas, 30 diameter and 15 pieces of it sorted like an X in the middle in the desert. So these are big antennas. But if you read this sentence, you see you have to size the sending antenna too. So if you need a high bandwidth, your craft, which is moving into space, always needs a larger and more powerful and more energy-based antenna to transmit the same amount of data that it was transmitting by half the distance. So this is something you have to keep in mind because energy is something you don't have in a spacecraft. The best energy option you have in a spacecraft is an isotopic generator. It's called RTG. Most people say, hey, use solar panels. Solar panels are great, but they have some problems, some side effects. First of all, sometimes you don't have direct sunlight, but that's not the biggest problem. The biggest problem is that solar panels